Thank you, Rick. Good morning, everybody. Thank you so much for coming. My talk today is going to be a lot less technically focused, but rather we're going to talk about the challenges of administration and setting up collaborative industry consortia. So just a bit of, so this is a talk that is co-authored by Kim Runge, who along with me is a technical co-director of the Collaborative Consortium for Coarse Particle Processing, which I will talk about shortly. So in terms of the global copper industry, the global consumption of copper over the next 25 years will exceed that of all copper ever mined to date. This is quite an oft-quoted statement by Robin Badaham, Australia's chief scientist. Australia, for example, produces approximately 13% of the world's copper, but the companies that we deal with are not just Australian, but span the entire globe. And the industry, as Rick quite nicely described in the introduction, faces a number of challenges: declining ore deposits, pressure to engage in much more sustainable practices in order to preserve the environmental for all of us. And according to the Altalay roadmap from Chile, the world's largest copper producer, the current condition remains unchanged. Copper production will gradually begin to decline around the world. And so, again, from Robin Badaham, the advent of technology for processing coarse particles by flotation is seen as one of the foremost areas where significant improvements in mineral processing are possible. And with that in mind, we decided to start to focus our efforts on integration of technology for processing coarse particles. Why do we bother to process coarse particles in the first place? Well, you can achieve some purely technical achievements, such as increased throughput through the plant. Up to 25% for copper ore has been demonstrated. There are some very substantial energy savings, particularly because you do not have to grind particles quite so fine, and comminution takes up the majority of energy expenditure within minerals processing. Of course, reduced energy means reduced greenhouse gas emissions, means a mitigation of the global warming effects or global climate change effects. We are also going to be improving dewatering performance. If your particles are much coarser, they are much easier to dewater to the point where you can dry stack them, and potentially completely eliminate things like catastrophic tailings dam failures. We are also going to be reducing acid mine drainage risk and the risk of water pollution to groundwater aquifers. There's a potential for increased revenue through reduced losses, because in conventional flotation, quite an amount of metal is lost to coarse tailings. And finally, what we can do is we can improve the viability of access to new bodies, or bodies that would otherwise be deemed uneconomic to process. And with that, enter the HydroFloat technology by Area's flotation division. This technology is not new. It's been around for quite a while, and it represents quite a radical, a very radical departure from the design of a conventional flotation cell. It has a very quiescent, in other words, low turbulent hydrodynamic environment. Particles are suspended by means of a fluidized bed, and what you do not have is this conventional froth cap that you usually see on top of flotation cells. All of that, without going into too much technical detail, makes it highly conducive towards improved recovery of coarse particles. And this is an example from a site done at KDL by Newcrest, where it shows where in conventional flotation, the unit recovery of gold decreases with increasing particle size until it hits about 100 micron, where all recovery pretty much comes to a grinding halt. The only other currently used widely applied technology is that of gravity separation, which shows quite poor performance for particles that are finer than 200 microns, and after that slowly starts to pick up. But with the use of the HydroFloat technology, what was seen is that you are able to fill in the gap between conventional cells and gravity separation, where you can achieve some really good recoveries in this coarse particle flotation range between roughly 200 and 600 micron. So again, HydroFloat is not new. It has been around for approximately 17 years, and it is commercially available. And there are a number of installations that are now starting to employ it at full scale. One of them is Newcrest Cadia site, where Newcrest is one of the leaders, global leaders in this particular area. But also operations such as Rio Tinto, Anglo Platinum, and others are now looking at full-scale installations at some of their sites. But what became apparent as these full-scale installations started to take place is that even the most promising new inventions cannot achieve wide-scale change if they are not properly implemented at full scale. And what became apparent is that a very substantial amount of work is still required to achieve sufficient technology integration in order to make these fabulous new inventions actually provide output in practice. So, because so much work needed to be done, we proposed forming a collaborative consortium with industry, which we called the Collaborative Consortium for Coarse Particle Processing, or CPR for short, where we aim to enable both efficient and coordinated research efforts that are aimed at producing practical and applied solutions to industrial issues surrounding coarse particle processing, with a particular focus, but not exclusively focused on areas HydroFloat technology, with very active support and participation by areas flotation division. So the research disciplines and objectives of this were quite ranging. We were looking at maximizing coarse particle recovery, predicting recovery, optimizing circuits, evaluating techno-economics and scale up. And we're looking at also a range of key research disciplines, ranging from process model development, mineralogy, chemistry optimization, optimization of physical cell units, and industrial process design. So why do we want to do things in collaboration? Well, collaboration is good for everybody. It provides streamlined and coordinated research efforts and to form and enhance the outcomes of individual projects rather than doing projects on a one-by-one basis. Joint funding for projects that are of common interest can result in much more efficient use of financial resources by the funding companies. Cost sharing of common interest projects means that more funds can be freed up for doing special interest projects on one-on-one basis with companies. Most importantly, we avoid duplicating effort because we can see what is happening across the board and we can avoid repeating ourselves across multiple projects, but most significantly, produce much higher returns on individual research investment from mining companies, where a single financial contribution provides you with access to the results of a number of research endeavors. As a side effect, but is also quite important, is that we wanted to produce a knowledge hub that is centered here at the Sustainable Minerals Institute that would give external companies access to world-class expertise in every aspect of this particular discipline, so cross and transdisciplinary, state-of-the-art equipment that is purpose-built for applied research needs, such as this really nice pilot rig that was built by Connor Edemir. And we also want to produce a pool of highly skilled potential employees. As we produce HDR students, those would then go off into the wider world and join industrial operations as fully fledged experts in this particular field. So that's a very nice idea in theory. So in practice, how do you go around and build a consortium? Well, if you read a book on how to build a consortium 101, this is actually quite a widely studied area of research in its own right. So building industry university collaborations, if you go and look it up in the literature, you'll find books on it and papers. One of the most popular modes of doing it is called the Mitsubishi model, where if you follow these 5 easy steps, where you identify partnership, make contact, partner assessment, you negotiate and you sign the agreement, you too can form your very own industry collaborative consortium. Unfortunately, like with all such things, the reality is far more messy. So how long does it take to build an industry consortium? It takes 3 years. And it starts off with a big idea, and to that we have Kim Runge to thank, who had the strategic foresight to actually start and initiate a strategic research project in this area, which we have managed to obtain co-funding from Newcrest Resources, as well as Areas Flotation Division, which was later bolstered by the Complex Ore Bodies Program. Approximately a year into that project, it was decided to start initiating the proposal process for building the collaborative consortium. And that particular process of setting it up was also quite strongly subsidized and supported by the Complex Ore Bodies Program. We have spent several years interviewing potential sponsors and then tailoring the program itself, as well as the technical composition of said program, to the individual needs of the sponsors, and going round and round with a number of iterations where we held some in-person workshops. We have gone back and forth on the structure and the contractual setup of the consortium. We have gone through a number of different iterations of the proposal along with the project. We actually ended up having our very first kickoff meeting in June this year, which was 3 months prior to the actual signing of the agreement, because negotiations of a contract are very time and energy consuming. And then finally, on October 16th this year, we have formally signed the program agreement and have kicked off the formal commencement of consortium activities, even though unofficially we've been running for a few months already. And when that happened, we were famous for about 5 minutes, which was quite nice. But then there were quite a few key lessons that were learned as a result. And the first one is that you really, really have to make a very important choice of the technology of focus as well as a main partner that you are going to team up with. In this particular case, our main team partners were Areas Flotation Division and Newcrest Mining. And based on that, we have built this consortium up to what it is today. It is very important to invest in the strategic area. In other words, you need seed research, but you also need seed setup funding, and both of those were contributed to by the Complex Ore Bodies program. This process is continuous and it is iterative and highly, highly messy. It is also very important to have face-to-face interactions between all parties, but if you discover yourself amidst a global pandemic, you do find that you are able to cope using Zoom. It's not the best, but it's doable. And finally, the program needs to be flexible in order to carefully address the individual needs of all the participants. If you try and make it a one-size-fits-all arrangement, you are not going to satisfy as many people as we've been able to do. It makes it much harder to organize, but at the same time, it reaps much greater rewards. And the contract agreement is absolutely the hardest part. And whenever you start your consortium negotiations, you start with drafting the contract agreement before anything else happens, because it will be the longest and the hardest part of the entire process. So what does our program actually looks like now? What we've got is we've got Neville Plint, who is a program chair, and Kim and myself are the technical directors. We have a steering committee that is made up of a number of sponsor companies. So Newmont, Anglo American, Newcrest Mining, Areas Flotation Division, Hudbay, and Glencore. We also have some non-voting sponsors such as RS Resources as well as Complex Ore Bodies. We have a wonderful dedicated team of researchers that are working on a number of projects across the program, and of course our wonderful administrative team, without whom none of this would have been possible. In terms of the technical content of the projects, I won't go into that in too much detail. We are currently sitting at a selection of about 10 different projects that range between purely researcher-led to those that are PhD projects. We put on several candidates and the steering committee made the final choice of projects. The project choice isn't quite complete. We have selected 8 out of 10, and the ones that are highlighted in orange will go forward if we secure more funding, which we're certainly hoping to do. Some of the work focuses on really not just implementation and applied work, but some of the more cutting edge scientific concepts. We've got some wonderful work going forward with Angus Morrison and Dion Hugo, looking at computational modeling, as well as really advanced techniques such as PEPT for characterization of hydrodynamics within the HydroFloat unit, which will help us to understand it on a number of different levels. Again, I won't go into that in too much detail because I'm running out of time. And so we are off on our adventure. We have worked hard for 3 years, and we are now at a point where we can finally start doing some research, and we're very, very happy about that. And there is a tremendous number of people to thank. First of all, Areas Flotation Division, Newcrest Mining, and Complex Ore Bodies program for funding that initial research project that started everything. Complex Ore Bodies for providing seed funding for program setup, which was extensive and very labor intensive. The Sustainable Minerals Institute and the JKMRC for their continuous support for the setup efforts, and all our wonderful, engaged, and very demanding sponsors, RS Resources, Anglo American, Areas Flotation Division, Glencore, Hudbay, Newcrest Mining, Newmont, and Complex Ore Bodies. Our lovely business manager, Astrid Whitbread, our wonderful and amazing RPM, Trish Murray, and of course, our entire research team, without whom, again, none of this would have been possible. Thank you very much.
Waiting for this mic to connect itself up, which I should have done earlier. Can everyone? Yes. We actually have time for some questions, believe it or not. Thank you, Lisa, for being on time and organized and so on. So does anyone, I'll keep an eye online. Anybody who has questions online, please type them into the Q&A. And if do we have any questions in the room, please put your hand up and we'll bring a microphone to you.
Lisa, 3 years in the making. What's the sort of timetable and schedule of the project going forward? For how long does it last, etc.?
Okay, so the program is nominally 5 years long, in which time some of the projects have already commenced, but others have 5 years to become executed. But we have, however, built in some additional space into the time in which the program can be completed to allow for potential delays with HCR programs, as one has to do. There is also, now that the program has officially commenced, there is a 2-year window where new sponsors can come on board, which means that the whole runtime of the program can get extended by an additional 2 years. So currently we're looking at 5, possibly 7.
I don't see any questions online yet. Oh yes, there's one. Just wait a second. Yes, there's one in the chat. Are you looking for researchers to join the group?
In the future, currently, not right now. We are fully organized, but we are always looking for new talent. And as soon as we have come up with a plan to employ said talent on new research that we have not yet allocated funds for, yeah, always.
But is it I should know this, but I can't remember. There are PhD projects involved.
There are PhD projects involved, and we have the application to apply for PhD scholarships, I believe, closes tomorrow. So, and yeah.
So yeah, if you want a PhD, you've still got time.
You still
Anybody?
have 1 day to apply for a PhD program.
Okay, and we have a question in the Q&A. From Maida, actually. Thanks, Lisa. How is the coarse flotation applicable in complex ore bodies which often contain disseminated minerals?
Right. So in case where your minerals did not occur in very large grain sample, so you're not talking about wanting to recover a particle that is fully liberated and is 600 microns long, wide, because I'm told you can do that using conventional technology. You can still recover very coarse particles that have a very low level of surface liberation. So some numbers suggest you can go as low as 5% surface exposure for coarse particles, which can still be the case with very finely disseminated minerals, where you can put that process up front and early reject your gangue minerals early, and hence pre-concentrate your stream that goes towards conventional flotation process that goes through regrind, etc. So doing that will represent a very substantial energy saving, because you do not have to finely grind your entire process stream, but only a pre-concentrated portion.